Welcome back to The Explainer. So glad you're here. Today, we're diving into the ingenious, highly specific defenses built into massive marine generators. Now, looking at these giant machines, they seem pretty much invincible, right? Heavy steel, copper, engineered to power vessels through the harshest oceans on the planet. But the reality? They are incredibly vulnerable to unseen threats. Today, we're focusing specifically on sleeve bearings and shaft current protection, the exact mechanics keeping these powerhouses alive.
So what is a generator's true hidden killer? When we think of catastrophic failure, we usually picture, something dramatic. A massive short circuit, a fire, maybe a huge mechanical explosion. But honestly, the biggest threats to a marine generator's lifespan aren't those massive, noisy events. More often than not, they're silent. They're invisible forces striking from within the machine itself, just slowly degrading its most critical moving parts until the whole system literally grinds to a halt. Let's talk about our first invisible enemy, shaft currents. Now, by their very nature, large generators produce incredibly powerful magnetic fields. And sometimes those fields induce stray, unintended voltages right into the rotating steel shaft. If you leave this unchecked, those voltages drive invisible electrical currents that circulate down the shaft and arc straight through the bearings to reach the ground. And here's the crazy part. Every single time that current arcs, it microscopically melts the metal. We call this pitting. Over time, this silent electrical storm completely destroys those perfectly smooth bearing surfaces. It leads to severe friction, overheating, and eventually total mechanical failure. It is, without a doubt, the ultimate invisible enemy.
Section 1. Blocking the threat. Let's look at the end bearing. So how exactly do marine engineers stop an electrical current that's running through solid steel? Well, they use a deceptively simple solution. Standard construction in these machines uses split-type sleeve bearings to support that heavy rotor, but the bearing on the non-drive end, which we call the end, is uniquely engineered. It's electrically insulated from the rest of the generator frame. By inserting an insulation barrier right at this specific end, engineers literally break the circuit. The shaft currents simply have nowhere to go. They can't circulate, and because of that, they can't arc through the bearing and pit its surface. That single, unassuming ring of insulation is a literal firewall against electrical degradation.
Moving on to Section 2. Absorbing mechanical stress. The D-end bearing. Now, if we transition to the completely opposite side of the shaft, the drive end, or D-end bearing, has a totally different job. It doesn't just hold the shaft up. It connects the generator to the outside world. This bearing is spherically seated, which is just this elegant piece of mechanical design allowing it to self-align during assembly. Why does it need to do that? Well, because it has to absorb brutal mechanical stress from whatever the generator is coupled to, like, say, a massive diesel engine. Look, even the most perfect installation is going to have tiny misalignments between the engine and the generator. If the bearing was perfectly rigid, those coupling misalignment loads would just tear the machine apart through vibration. So the spherical seating lets the bearing yield just enough to absorb that stress smoothly. It's brilliant.
Let's put this side by side to build a complete picture of the rotor support. Check out this contrast. On the left side, we've got the end bearing. This is essentially our electrical bodyguard, fighting off invisible shaft currents through specialized electrical insulation. Then, on the right side, we have the D-end bearing, acting as our mechanical shock absorber, fighting physical stress via spherical seating. These bearings might look pretty similar from the outside, but their dual opposing functions really show just how perfectly tailored each end of the shaft is to its specific, dedicated enemy.
Section 3. The Protective Accessory Suite. Time to fight environmental threats.
Because, physical bearings just aren't enough on their own. There are exactly 4 critical accessories that round out this machine's baseline protection package. Let's break down what they are and why you absolutely need them.
All right, here's your ultimate accessory checklist for marine generator health. First up, PT100 sensors. These are highly accurate temperature probes embedded directly into the stator windings and the cooling air paths. Basically, they act as the machine's nervous system, warning you of overheating way before it's too late. Second, space heaters, which we'll actually dive into in a sec. Third, leakage water indicators, because, let's face it, mixing raw cooling water with high voltage is a massive recipe for disaster. And fourth, continuous oil lubrication units specifically for the motors, ensuring those precise bearings never, ever run dry. This entire suite is exactly what keeps a marine generator healthy between those major overhaul intervals.
Which brings us to Section 4. Real-world check. The condensation threat.
Let's apply all this to a highly realistic operational scenario. Imagine this, right? A ship is at anchor. and a massive marine generator sits idle, completely powered down, for 2 straight weeks in humid, sticky, tropical conditions. It's not running, so it's not generating any of its own heat. What specific accessory out of that suite we just discussed prevents condensation damage during this dormant downtime?
The answer: the space heaters. And the physics behind this are actually pretty fascinating. When a machine is idle in a humid environment, the ambient moisture naturally wants to settle on the cold metal and copper inside. If moisture condenses on the stator insulation surfaces, well, it can create a path for a massive short circuit the literal second you start the machine back up. So the space heater's job is passive, but absolutely vital. It turns on when the machine is stopped to keep the internal windings just above the ambient dew point. By controlling that thermal dew point, moisture is physically stopped from ever condensing on those sensitive electrical insulators. Pretty neat, right?
Section 5, the complete package. Let's get our defenses mapped.
Let's pull all these moving parts together into one clear picture. Every single component in this architecture is an active defender with a very specific mission. Operational threat: shaft currents. The engineered solution: electrical insulation. And the component focus is that end-end bearing. Next threat: coupling misalignment. The solution for that is spherical seating, which is housed in the D-end bearing. And finally, the threat of tropical humidity and condensation is completely solved by thermal dew point control, executed flawlessly by those space heaters. Everything has a purpose. Literally nothing is left to chance.
So, we've essentially built the ultimate defensive package on paper. We've protected the machine from electrical pitting, mechanical stress, and environmental decay. But before a shipyard or a ship owner trusts this multi-million-dollar asset out on the open ocean, how do they definitively prove it's actually fit to go to sea? Well, the answer lies in the rigorous gauntlet of the full testing suite, which is exactly what we're going to dive into in our next explainer. Thank you so much for hanging out with me today. Keep asking questions, keep exploring the mechanics of the world around you, and I will catch you in the next one.